Alright, so here we have a question that we have to deal with the drag force, and we only have to set things up. We don't have to be able to solve all the calculus. We just have to be able to organize the equations that would be solvable. So this is kind of like the baseline of what you have to do if you see a drag force or a force proportional to velocity in some sort of problem. Anything more than that is great, but definitely be able to do at least these steps. So part A, we have a ball. And we need to think of and draw in all the forces that are acting on it sometime before it reaches terminal speed. So it's falling through the air and approaching the ground. So it's got a weight. So that's kind of the obvious one, right? Call it weight, call it force of gravity, whatever you want. But we also are told that there's a drag force. We can't ignore air resistance. And since the ball is moving down, the drag force always opposes the direction of motion, right? So up. And I guess I should do one thing that's a little bit more detailed, right there. Kind of like that. You notice I've drawn the drag force vector shorter than the weight vector because we're told it's before it reaches terminal speed, so the net force has to point downward, still accelerating down. And that's it. There's only two forces. It's just falling downward, and that's all. So it's pretty simple. So that's part A. Part B. State whether the magnitude of the acceleration increases, decreases, or remains the same as it approaches terminal speed. So there's a couple different clues to this. The first is just the word terminal. Terminal means like the final speed. Once it reaches that, it doesn't change. So once it reaches terminal speed, the acceleration must be 0. There's another way to think about it too. As it reaches terminal speed, it's starting from 0 velocity. You drop it off the cliff. So at the start, at the initial time, the drag force is 0, and the weight is the only force that causes it to accelerate. So we can kind of approach this in a couple ways, and I think the easiest way is to deal with it in the sort of the force perspective. So this is also a written part. So the first thing is that the acceleration decreases. Now that's the conclusion. And so we start at v equals 0, so the drag force equals 0. And as we fall, we speed up. So as v approaches v terminal, the drag force increases. Since the drag force and the weight force are in opposite directions, as the drag force increases, the net force must decrease, right? Because the weight doesn't change. So we're sort of canceling out more of it, right? And so as the net force decreases, the acceleration must also decrease, right? Okay, so now we have the actual math part. We need to write but do not solve a differential equation for the instantaneous speed of the ball in terms of the time, given quantities, and fundamental constants. So this step, whenever you see differential equation, you should be thinking there's going to be d something dt, right? That's the first picture that has to pop into your mind, is I need an equation that has something like that in it. And then the second thing is to use the question that we've kind of done prior now to think about it, right? We drew a free body diagram, and we talked about accelerations. So that's kind of leading us to think that maybe we should do something with F equals ma. And really, this is, any question about drag forces, this is going to be your starting point. The math afterwards is tougher, but it always starts from Newton's second law. So the force, right, this is the net force. So we did that in this figure. So I'm going to call the positive direction up. And in that case, we have d minus w is ma, negative, because we are accelerating downward. Right, so the weight and the acceleration have the same sign. Now we plug in what we know. b v squared minus mg equals negative ma. And here's the differential equation part comes in. We have to recognize there's another way to write the acceleration related to the velocity, and that's if it's the derivative of velocity. So bv squared minus mg equals negative m dv dt. And now we just need to solve to get the derivative part equal by itself. So dv dt equals, so if we divide by negative m, we're going to flip the order of the terms on the other side. So we get g minus b over m v squared. And that's the final answer. You can write this as an integral. However, it's not as simple as writing this. So I'm clarifying, this thing in blue here is not a correct thing to do. You can't integrate, actually, sorry. Right. You can't integrate it like this and say that v equals the integral of g minus b over m v squared dt. This would not be right. You have to do another process called separation of variables, which for something like this is a little bit tricky because you have this term floating around, but this does not work. Just leave it as a derivative. There is an integral form that you can write it as. This is not it. Really, you shouldn't even try. It says don't solve. So just once you get to this, that you have a derivative part, that's the differential part, then you're done. This could be solved for v of t if you wanted to work through it. And so finally, back to some sort of relatively straightforward math in part D. Terminal velocity happens, terminal velocity happens when a equals 0. So we wrote f equals ma, and at the terminal velocity point, we know what the net force is. We have bv squared up, mg down, and this is 0 when v equals vt. So now all we just need to do is solve, and it's a pretty easy thing to solve. Or vt is the square root of mg over b. Right? And that's it for this one. The tough part is really in part C, setting up that equation. And then that's the thing that this problem is meant to practice.